Let me get back to the PowerPoint here. All right. So what we're going to look at now, very important skill for you to master, and that is how do we balance redox equations. Now, this is kind of different from how you balance a normal equation. In fact, you could use what you learned in order to, back then, in terms of balancing equations, to balance redox equations. But in some cases, it can get real messy, real difficult. So there's another systematic way of going about balancing specifically redox reactions, right, or redox equations. So the best way to learn this is to go through the steps using an example. An example we use here is the oxidation of Fe2 plus to Fe3 plus by the dichromate ion. Now, admittedly, this is not enough. Yes, sir.
Sorry, is there any way you could like secretion?
You mean like this?
Yeah, just like.
Oh, I think I don't know how to do that. I mean, this is the best I can do for now. Okay, so this example we're going to look at is the oxidation of Fe2 plus to Fe3 plus by the dichromate ion. Now, the information here, to be perfectly honest, is not enough for you to answer this question. So what I'm going to do is basically write down the unbalanced equation. I hate reading. So this is the unbalanced equation. I'm going to help you. Fe2 plus the dichromate Cr2O7 2 minus to give Cr3 plus Fe3 plus, right? So this is what you're given, or what you could be given in a question, right? And the question is asking for you to balance this equation, all right? So let's go through the steps. Well, the first step I actually just did, right? It says write the unbalanced equation for the reaction in ionic form. So this is the equation right here, all right? The unbalanced equation. So that's the first step. The second step, oh, and they did it for us here as well. So I'm sorry?
What's the number of bits here?
What's the number?
The products, the CR.
3 plus?
Up above where you wrote it.
Yeah.
Oh.
Is that 3 plus?
It's the same thing, 3 plus, yeah. But I need to remove this thing here. Okay. Sorry about that. All right, so that's the unbalanced equation. Now, in some instances, you may be given you may be given a description of the reaction in words, in which case you have to figure out what would be the unbalanced equation, what would be the reactants and what would be the products, right? So that's the first step. The second step is that you separate this unbalanced equation into 2 half equations, right? One half equation would be the reduction and the other half equation would be the oxidation, right? So this is how you do that. As far as the oxidation is concerned, that would be the Fe2 plus to form Fe3 plus, right? Of course, that's oxidation because the charge or the oxidation number of the iron is increasing. And then as far as the reduction half equation is concerned, that would be the Cr2O7 2 minus to form Cr3 plus, all right? So those are the 2 half equations that you would have obtained by the separation of the unbalanced equation given or that you have figured out initially. Okay, so the third step is that you balance all atoms excepting oxygen and hydrogen in each half equation. And the way you do that is in the traditional way that you're accustomed to when it comes to balancing equations, right? Now, as far as this equation is concerned, there's only one ion on each side, right? So we don't need to make any changes here. But for the second half equation, you have 2 chromium atoms here, and you have only 1 here. So, what, you have a question? You're gonna do what? You're gonna see later on. It's gonna come up later on in the latter steps, all right? But that's a good question. So, as I was saying, you have 2 chromiums here, you have 1 here. So what do? We put a 2 here. So therefore, to balance the chromium, we put a coefficient of 2 beside the Cr3 plus to balance with the chromium, the 2 chromiums on the left side, all right? So that's a very important step. Make sure that you balance all atoms excepting oxygen and hydrogen. In some cases, you may not even need to balance any other atom because those atoms are already balanced. But in this case, in the case of the chromiums, it is out of balance because you have two on one side, one on one side. So therefore you need to balance it by putting two in front of the coefficient, or the coefficient of two in front of the CR3 plus on the right side. So that is step number 3. Step number 4. Now, for reactions in acids, and that's what we'll be dealing with in this class here. To balance the oxygens, to answer your question, we add water to the side that is deficient of oxygens, and we add enough water so that the number of oxygen atoms are the same on both sides. And then to balance the hydrogen atoms, we add hydrogen ions to the side that is deficient of hydrogens until they are balanced on the same on both sides as well. All right. So what that means in the case of this equation, that seems faint. Can you see that?
Not at all.
All right, let me see if I can change the color on that. Well. Well. Okay, so let me go back to full screen here. Okay, so in the case of balancing the oxygen in this case, because we have 7 oxygen atoms on this side, what we do according to this step is that we add 7 water molecules to the right side, right? And the reason why is because by adding 7 water molecules to the right side, you have now added 7 oxygens to this side, which balances with the 7 oxygens on the left side. And then now to balance the hydrogens, according to the instructions here, we need to add hydrogen ions. And in this case here, because we have 14 hydrogen atoms here, we add 14 hydrogen ions on the left side to balance the 14 hydrogen atoms on the right side, right? So this is very important, right? First, you balance the oxygens. How do you balance the oxygens? By adding water molecules. So you look on both sides to see which side has a greater number of water molecules, and you add the water molecules to the side with the lower amount, right? And you add enough water molecules so that the number of oxygens on one side is equal to the number of oxygen atoms on the other side. And then after that, we balance hydrogens. How do you balance the hydrogens? By adding hydrogen ions to the side which needs it, right? So in this case here, you have 14 hydrogen atoms on the right side. So you balance it by adding 14 hydrogen ions on the left side. And that's basically how you balance both the oxygens and the hydrogens, all right? Step 5. Now, this is where students tend to screw things up because they tend to add the electrons to the wrong side. But let me read the rule here. It says you want to add electrons to one side of each half reaction to balance the charges of or on the half reaction. So basically, the charges are not balanced in each case, right? In this case, for example, you have 14 plus charges minus 2, so you have plus 12 here on the left side, and you have a total of plus 6 on the right side. So the charges are not balanced. We need to have the charges balanced, right? So what this rule is saying is that you need to add electrons to one side or the other until the charges on both sides for each half equation is balanced or are the same, all right? So what does that mean? That means that in the case of this half reaction here, remember now you have 2 plus charges here, you have 3 plus charges on the right. So if you want to balance charges, you add 1 electron here, because one thing you need to keep in mind, each time you add an electron, you're adding a negative charge. And by adding a negative charge, you're reducing the total charge on that side by 1 for each electron added. So because this side had a total of plus 2, and this side has a total of plus 3, then you add 1 electron to this side, so you're adding a minus 1 charge here, and this now becomes plus 2, which is equal to the plus 2 on that side, right? So the key thing you need to remember here is that the electrons are added to the side with the net higher charge, right? One side has +3, the other side has +2, so you add electrons to the +3 side, so as to reduce that side until the total charges will be equal on both sides. Let me clear this here. And then for this equation here, right, as I said before you add the electrons, the total number of charges here will be +12. The total charge here will be +6. So what does that mean? That means we need to add 6 electrons to this side, because by adding 6 electrons, you're adding 6 negative charges. So this side becomes reduced to +6, which balances with the +6 on the right side. All right? So just to recap, because like I said, the most common error I've observed when grading students work on this is that they add electrons to the wrong side. All right? So please remember that you add electrons to the side which has the higher net charge. And then you add enough electrons until that side's net charge is reduced to the same number of charges on the other side. And that's why you get the charges balanced. Yes, sir.
So there's ions.
No. No. Because those are molecules. Okay, any questions about step 5? Any questions? Any questions? Okay, we're not finished yet. Couple more steps involved. Because now we have to take into account the fact that for this half equation, the number of electrons is 1, and here we have 6. And that's a problem, because remember I said that in every redox reaction, the number of electrons lost and gained will be the same. That's not the case here, because we have 1 electron being lost here, and we have 6 electrons being gained in the second half equation. So what do we need to do in order to make sure that the number of electrons lost and gained are the same? Well, according to this step, what we need to do, if necessary, because sometimes it's not necessary, we equalize the number of electrons in the 2 half equation by multiplying the half reactions by appropriate, and I probably should say integers, right? And not coefficients, all right? So make a note of that. That should be by appropriate integers, right? So what does that mean in this case here? In order to get the number of electrons lost here being equal to the number of electrons gained here, we'd have to multiply this entire equation by 6, right? So you would have a 6 here, and most importantly, a 6 here, because now we're gonna have 6 electrons here, which will be equal to the number of electrons gained here. So this will be the result. You're gonna have this equation here, multiplied by 6 to give you this, all right? And then, after doing that, then we simply add the 2 equations together. So now we have a situation where the number of electrons lost and gained are the same. So when you add these 2 equations, those 6 electrons will cancel out, and what you'll be left with will be the resulting equation. Straight again. I'm sorry about that, folks. Let me okay, leave it at that. All right, so let me go back to full screen. All right, so now you're going to add these 2 equations together, and as I said before, these 6 electrons will cancel out with those 6 electrons, like so, and then you simply write down what is left, and that would be the final answer. All right, that would be the balanced redox equation. However, I would strongly suggest, right, that even though you might be confident that this might be the correct answer, that you do one final check through to make sure that everything is balanced on both sides in this final equation, right? So you look at all the atoms of each element to see if they're balanced. And also you look at whether or not the total charges are balanced on both sides. So if we do that, you see that in the case of hydrogen, we have 14 hydrogens here. We have 14 here, 7 times 2, so that's balanced. We have 2 chromiums here. We have 2 chromiums here, so that's balanced. We have 7 oxygens here, and we have 7 oxygens here, so that's balanced. And we have 6 ions here, 6 ions here, that's balanced. And then we have to look at the charges, right? So as far as the charges are concerned, you have 14 plus charges, 14 times 1 minus 2, 6 times plus 2, I'm sorry. So when you add up this here, the total charge on the left side would be 24. And then on the right side, you have 6 times 3, which would be 18 plus 6, 2 times 3. And 18 plus 6 will give you 24. So the charges are balanced as well. All right. And that's basically confirming that you have actually successfully balanced this redox equation. All right. Now there's one more step that that is mentioned here. I won't go into that. I usually leave that for my Chem 2 students. All right. It talks about doing the same thing for basic reactions, but I'll leave that alone for now. All right.
Any questions we give, we'll have. Regarding this, we'll have the. Ionic charge, the +2, +1.
Yeah, yeah.
Okay,
Yeah, you'd have to be, that would have to be given to you in order for you to be able to solve problems of this type, all right? Okay, any other question? Oh, last slide, I'm sorry. Oops.
What I said if we needed to equalize the number of electrons to the times each side by the. same.
Oh, so you're talking about here,
Yes, thank you.
and then you multiply the first equation by 6. Okay. Yes, ma'am.
Hydrogen, why did they write that as 14 hydrogen and not like 7 H2?
Because you mean here compared to here?
Just thought, I thought hydrogen was diatomic, but I had substitute.
Well, it has a subscript of 2 here, but what we're looking at is the total hydrogen count on both sides. So no, don't worry, we take that into account. The 2 times 7 gives you 14. And that's the reason why we add 14H plus on this side.
I understand why it's like, I just don't get why it's right, that's to H instead of like 7 H and like.
Oh, well, that's basically how the steps are. To balance the hydrogens, you add H plus, not H2 or just H plus. Right, exactly. All right. Yes, sir.
Do you guys? Wow.
The previous, oh, you mean the last,
Yeah,
the one following this?
Yes.
Okay.
On the final equation, does it matter the order sides, right?
Does it matter what?
Like the order of the. Like.
As long as they're on their
on the
respective
sides.
sides, right, exactly. It doesn't matter what the order is. All right, any other questions? Any other questions? You look puzzled. What's up? Well, remember, we're talking about redox reaction, right? In every redox reaction, you have electrons leaving something and going to something, right? So first you have to figure out, you'll notice, where was it? You'll notice that at this step right here, step number 5, we have to figure out what is losing electrons and what is gaining electrons. And the way we do that is that we look at the total net charge on either side for each half equation, right? So for example, in the case of this equation here, previously we had Fe2 plus on the left side and Fe3 plus on the right side. So the question is, okay, where is the electrons being added or lost, right? And in this case, we figure out that the electrons will be lost as the Fe2 plus is converted to Fe3 plus, right? Conversely, for this equation, we figured out that the electrons are gained on this side, right? So that means that the Fe2 plus is losing electrons, and the electrons will be gained by the 14H plus and the Cr2O72 minus to get their respective products, right? So that's what happens in every single redox reaction. Electrons are leaving something and going to something, right? You cannot have oxidation without reduction, right? If you have one taking place, then somewhere in the universe, the other one is taking place. Because if the electrons are leaving something, they have to move towards something, all right? Okay, any other questions before we move on? Any other questions? Yes, ma'am.
I was going to some calculations, but like, how do you come to 6 electrons on those and like what do you have?
You mean, how do I come to one now?
The number 6 electrons for the
Here?
second half.
Okay, so the reason why we had 6 electrons here is that before we added those electrons, the total charge here on the left side would be 14 minus 2, which would equal to plus 12, right? The total charge on the right side would be plus 6, 2 times plus 3. The water does not provide any charge, right? So therefore, we have plus 12 here, we have plus 6 here. So the question is, to which side would the electrons add, right? Or to which side would you add electrons? And the answer is you add electrons to the side with the net higher charge. So plus 12 is greater than plus 6, so that means that you add electrons to the side where the net charge is plus 12. How many electrons you add? Well, you add enough electrons so that the plus 12 is reduced to plus 6. That would mean that you'd add 6 electrons, which will give you a total of minus 6 added to this side, and therefore that would be equal to plus 6, which balances with the plus 6 on the right side. All right? Okay, so let's look at some other examples. We get out of this here. All right. Okay, so I'm just going to make up an example. Suppose you're given C. Okay, where is this now? Suppose you're given C2O4 2 minus plus MnO4 2 minus to form CO2 plus Mn2 plus. All right? Make sure that this works. Okay, good. All right, so that's the unbalanced equation. And you're asked to balance it, right? So if you recall, the first step in this process is that we separate this equation into 2 half equations. So one half equation in this case would be C2O4 2 minus to form CO2. And the other half equation would be MnO4. Oh, shoot, this should be minus. I'm sorry, not 2 minus. This here should be minus. So this is MnO4 minus to form Mn2 plus. All right? So that's the first step. We separate the equation into 2 half equations. The next step is that we balance all atoms excepting oxygen and hydrogen in the traditional way. Now, in the case of the half equation, the first one, you have 2 carbons here. You have only 1 here. So what do? We put a 2 here in front of the CO2 to balance the carbons, right? In the case of the second half equation, we don't need to do anything for the manganese because you have 1 here, you have 1 here, so therefore it's okay, right? So that's what we do in this step. We balance all atoms excepting oxygen and hydrogen. The next step is that we balance the oxygen by adding water when necessary, right? So in the case of the first half equation, you notice that you have 4 oxygens here. And here you have 2 times 4 oxygens, right? So therefore, there's no need to add any water to either side because the oxygens are already balanced in the first half equation. However, in the case of the second half equation, we have 4 oxygens here on the left side and we have none on the right side. So what do? We add 4 water molecules on the right side to balance the oxygens. All right, you want to see that? Okay, the next step. Oh, yes, sir.
Why do we get?
Because you have 4 oxygens here and we have none on this side. So we add 4 water molecules because each time you add 4 water molecules, you're adding 4 oxygens to this side, and those 4 oxygens will balance the 4 oxygens. Right? We balance the oxygens by adding water molecules. That's basically how we do it in this process. All right. The next step is that we balance the hydrogens, and we balance the hydrogens by adding.
8 hydrogen.
Well, let's deal with each half equation first. But remember, we balance the hydrogen by adding H plus, right? Ions. In the case of the first half equation, there are no hydrogens, so therefore we don't need to add any hydrogens. But as he was suggesting, I think, in the case of the second half equation, because you have 8 hydrogens on the right side, that means we add 8 hydrogen ions on the left side. And now the hydrogens are balanced. All right. So now we get to the part where, as I said before, students tend to mess up. We balance the charges, right? To balance the charges, we add electrons to the side with a higher net charge. So in the case of the first half equation, we have a total of -2 here, and over here we have 0, right? So my question to you is, to which side would you add electrons and how many would you add? Yeah, 2 on the right side, exactly, 2 electrons on the right side. Because by doing that, you're adding 2 negative charges, we'll end up with -2 there, all right? Okay, so now we get to the second half equation. Again, we have to look at the total charge on both sides. Now, if you look at the left side here, we have 8 plus charges -1. So that's a total of +7, right? And then on the right side, you have a +5 here, right? So my question to you is, to which side would you add electrons for the second half equation, and how many electrons would you add to that side? You have +7 on the left and +2 on the right. So to which side would you add electrons, and how many electrons would you add?
2 electrons to the left side.
Oh, I'm sorry, this should be +2, my bad. I think. This should be +2. What is that? This should be +2. Okay, so with that change, I'm quite sure you change your answer, right? So what would be to the left? How many electrons would you add to the left? 5 electrons, exactly, right? Because by adding 5 electrons, you're adding 5 negative charges, which reduces the +7 to +2, which balances with the +2 on that side. All right, very good. So now that we have balanced all the atoms and the charges, the next step would be to make sure that the number of electrons lost in one half equation would be equal to the number of electrons gained in the other half equation. So as we have it right now, we have 2 electrons being lost here and 5 electrons being gained here. So my question to you is, how do you equalize those numbers? How would you make sure that the number of electrons that is lost in the first half equation will be equal to the number of electrons that is gained in the second half equation? In other words, what do you multiply this equation by and this equation by to get the number of electrons lost and gained being the same? Sure about that? 4?
5 and 2.
I will multiply this one by 5. So you're gonna get 5 C2O4 2 minus to give 10 CO2 plus 10 electrons. And then I'll multiply this by 2 to get 10 electrons plus 16 hydrogen ions plus 2 MnO4 minus to give 2 Mn2 plus 8 H2O. All right? So once we have achieved that, then we know that the electrons will cancel out here and here, right? And there's nothing else to cancel out, so we just add what is left. So what do we have left? 5C2O4, 2 minus, plus 16H plus 2 MnO4 minus. So that takes care of things on the left side. And then on the right side, we have 10 CO2 plus 2 Mn2 plus 8 H2O on the right side. And that should be the final answer, right? But of course, as I said earlier, you should do a final check through to make sure that everything is balanced, including the charges, right? So let's do that now. 5 times 2, 10 carbons on the left side, 10 carbons on the right side, so the carbons are balanced, right? For the oxygens, it's 5 times 4, 20, 20 plus 2 times 4, 8, so that's 28 oxygens on the left side. And then on the right side, we have 2 times 10, 20, plus 8 oxygens, so the oxygens are balanced, 28 oxygens on both sides. Then we get to the hydrogens. We have 16 hydrogens on the left side. We have 8 times 2, 16 hydrogens on the right side, so that is balanced as well. Then we have 2 manganese here on the left side. We have 2 manganese here on the right side, so the manganese atoms are balanced as well. And then we have to look at the charges, all right? So let's look at the left side. How many charges do we have total on the left side? Minus 10 plus 16 minus 2, so that gives you what? 16 minus 10, that's 6 minus 2, that's plus 4, all right? And then on the right side, we have 2 times plus 2 plus 4. So the charges are balanced as well, right? So this equation is balanced. All right? Any questions?
It's the 10 carbons you balance.
Is the 10 carbons what?
Balancing the electrons.
Uh, That 10 comes from here. Where you multiply right through, you multiply this equation by 5. So you're gonna get 5 C2O4 2 minus, 5 times 2, 10 carbon dioxide, and 5 times 2, 10 electrons. So that's where this 10 comes from. And that 10 ends up down here.
Okay, it was 5 times balancing the electrons.
Exactly, right. You multiply that equation by 5 because you want to balance the electrons, right? The number of electrons lost and gained must be the same, right? Any other question? Any other questions? Okay, let's do maybe 1 or 2 more examples. Okay, suppose you're given you should get a little one. You are 3 plus NO3 minus. Okay. So based on the examples that we have looked at so far, what will be the very first step in this process? Okay. So that would be CrO4 2 minus to form Cr3 plus and N2 to form NO3 minus. Okay, what will be the next step? Okay, so that would be what? You said balance everything excepting oxygen and hydrogen, right? So that means you balance what in this case? The nitrogen. How would you balance the nitrogen? You put it to where? Okay, exactly. We don't need to do anything for the chromium because you have one on both sides, all right? Okay, what's the next step? Yes, sir.
Add water to review, like I said.
Okay, to balance oxygen, right? So to which side would you add water?
Nice.
Okay, and how many water molecules will you add? Exactly. What about this equation here? How do we balance the oxygen in that equation? We have no oxygens on the left, and we have 6 oxygens, 2 times 3, 6 oxygens on the right. So how would you balance the oxygens in that case? And what? 6 water molecules on the left side, right? Okay, what's the next step? After balancing the oxygens by adding water, the next step is to balance what? The hydrogens by? How would you balance the hydrogens? I'm sorry? Well, specifically adding H plus, hydrogen ions, right? So let's deal with the first half equation. To which side would you add the hydrogen ions and how many? 8, exactly. 8 hydrogen ions on the left side. What about the second half equation? To which side would you add the H plus ions and how many would you add? 12 hydrogen ions on the right side. Okay, very good. So now we get to balance the charge. Let's see if you can do this without messing it up. How would you balance the charges in the case of the first half equation? In other words, to which side would you add the electrons and how many electrons would you add? For the first half equation. I'm sorry? 4 electrons to the right side for the first half equation, is sure? How many charges total do you have on the left side? Plus 6, right? How many charges do you have total on the right side? Plus 3. So to which side would you add electrons and how many? 3 on the left side, right? Because by adding 3 electrons, you're subtracting 3 from 6, that gives you plus 3, which balances with the plus 3 on that side. What about the second half equation? Let me erase this here just to be. Okay. What about the second half equation? To which side will you add electrons and how many? How many charges total do we have on the left side? 0. How many charges total do we have on the right side? 12?
11.
11? Come on. You have 2 negative charges plus 12, that's what?
Oh,
Plus 10.
10.
Exactly. Okay, so to which side will you add electrons and how many electrons will you add to that side? 10 electrons on the right. So plus 10 electrons on the right. Okay, so with that said, what's the next step? Now that we have balanced all the atoms and the charges, what would be the next step? Okay, so how would you equalize the number of electrons lost and gained? In other words, what would you multiply this equation by, and what would you multiply this equation by, so that the number of electrons lost here would be equal to the number of electrons gained here? So you're going to multiply this equation by 10, right? So 30 electrons plus 80 hydrogen ions plus 10 chromate ions to give 10 Cr3 plus 4, not 4, what am I saying? 40 water molecules, all right? And then what do we multiply this equation by? 3. So that will give you 18 water molecules plus 3 nitrogen molecules to give 6 NO3 ions plus 36 H plus 30 electrons. And then we add these equations together and the 30 electrons will cancel out, right? But there's some other things that will cancel out as well, because we try to cancel out common items on either side of the equation. So what else do you think will cancel out? Okay, So in the case of the hydrogen ions, these 36 hydrogen ions will cancel out 36 of these, leaving behind what? 80 minus 36, so that's 44. All right, and then in the case of the water, you have 18 water molecules canceling out 18 of these, leaving behind what? That's what, 22? All right. So now we get to write down what is left. What is left is 44 H plus 10 CrO4 2 minus plus 3 N2. So that takes care of everything on the right, on the left, and then on the right, you have 10 Cr3 plus 22 H2O plus 6 NO3 minus. And as I said before, always do a final check through to make sure everything is balanced. So let's do that now. We have 44 hydrogens on this side. We have 22 times 2, 44 hydrogens on the right side, so that's balanced. We have 10 chromiums here, 10 chromiums here. As far as oxygens are concerned, we have 40, 4 times 10. And here we have 22 times, not times, plus 6 times 3, 18. 22 and 18, that's 40. So the oxygens are balanced. Here we have 6 nitrogens, so the nitrogens are balanced. And then as far as the charges are concerned, we have 44 minus 20, that gives you what? 18, no, what am I saying? 24. And then on this side, we have 30 minus 6, that is 24. So the charges are balanced as well. And that's therefore the balanced equation for this reaction. All right? Any questions about this? Yes, sir.
We take water to add oxygen.
That's just how how it works. There's another way of doing it where you add hydroxide ions, but I won't show you that method. But yeah, basically, these redox reactions always involve water along with either hydrogen ions or hydroxide ions. For all purposes, I'm just sticking to the method which uses water and hydrogen ions. In Chem 2, if you're going to have me or anybody else in Chem 2, then you'll definitely get into the basic environment where hydroxide ions are used. But I think that's a bit too much at this level, so I'm just going to stick to using water and hydrogen ions for balance. Any other questions? Any other questions? Okay, now you guys have assignment. Oh, yes, ma'am.
Is that 36 actually? It's crossed out.
You mean this? Oh, you mean this? This?
Yes.
Yeah, that's 36, yeah. Okay, so you guys still have assignment 4, right? So in assignment 4, let me go to bring it up. Okay, so if I remember correctly, did we do? Where did we stop the last one? I'm drawing a blank.
I think we just did 1 and 2 together.
Oh, we did 1 and 2. Oh, I didn't realize that. Okay.
I may have done it myself.
Okay, let's look at okay, let's take some time to do some of these. So number 3 says using the solubility table, predict whether each of the following compounds is soluble or insoluble in water. Now, if you recall, the solubility table is, see if I can bring that up. Tables. So that would be, I think it's the last page, if I'm not, or second to last page, right? This table right here, or this chart, right? This is what is used to make predictions as to whether or not a particular ion compound is soluble in water, right? So the question, going back to going back to the assignment, the question is asking to predict whether or not any of these or each of these will be soluble or insoluble or soluble in water, right? So let's start off with the NaCN, sodium cyanide, right? So based on the table, would you say that sodium cyanide is soluble in water? Here's the table. Sodium cyanide.
There you go.
Okay, so you're saying what, yes? Why? Because
The group 1A metals.
exactly, group 1A metal salts are always soluble in water, and sodium is in group 1A, right? So the answer for sodium cyanide would be soluble. What about B, strontium carbonate? We go back to the table again. SrCO3, strontium carbonate, would that be soluble or insoluble in water based on this chart right here?
Slightly salt.
Hmm?
Slightly, right? This is SR is the,
SrCO3. Oh, I didn't see this on here. So it says most carbonates, hydroxides, phosphates, and sulfides are insoluble. There are certain exceptions, right? It says here in the case of strontium, it says slightly to moderately soluble. I'll put that in the category of insoluble for the purposes of completing this assignment. So just put insoluble for the case of strontium carbonate, all right? And then now, what's the next one? Oops.
Lead.
Okay, the next one is lead acetate. Lead 2 acetate, I'm sorry. So let me go back to the tables. Again,
3B is insoluble, right?
for 3. Why do you say insoluble?
How about the-
Yes, for B, yeah.
Oh, you mean B? I thought it said C. B would be insoluble. Right,
C is soluble, right?
C would be soluble because
Acetate.
almost all acetates are soluble in water, exactly. Okay, and then what's the next one? Silver sulfide. Would that be soluble or insoluble in water? Insoluble because,
Silver isn't. Soluble.
say what?
Silver isn't soluble.
Or there, your second one says most chlorides, bromides, are soluble exceptions.
Well, that has to do with chloride, bromide, and iodine.
No.
Says exceptions of lead,
Right,
silver.
yeah, but those are, but we're talking about silver sulfide. What is more specific is this one right here, or what is to the, that would point to the right answer, is this line right here. Most carbonates, hydroxide, phosphates, and sulfides, right, are insoluble. There are certain exceptions, but silver is not one of them, right? So therefore, silver sulfide would be insoluble. In that case, all right? Okay, now, in the case of number 4, it says right balance, complete molecular equation, ionic equation, and then ionic equations for the reactions that occur when each of the following solutions are mixed. Identify the spectator ion or ions in each case, right? So I think we did some examples of this earlier. So let me help you with this one. Okay, so first thing I would do is write down, try to figure out what the molecular equation is. So Pb, NO3, 2 aqueous, and please do not forget the state symbols. It's very important when it comes to doing problems of these types. Aqueous, all right? So my question to you is, what would you expect the products to be in this case? Remember, it's a double displacement reaction, so basically the compounds will be switching.
Would it be lead sulfide?
Okay, lead. And more specifically, it would be lead two sulfide. Right, plus,
Your sodium, nitrate.
nitrate, okay, very good. And then we have to balance it, so how would you balance this? Okay, and then now we have to figure out the solubilities of these two compounds, so we have to refer to the chart. The same chart that we were looking at earlier. So based on the chart, let's deal with the lead sulfide first. Is that soluble or insoluble in water?
Insoluble.
Insoluble. So therefore, it will remain as a solid, right? What about the sodium nitrate? Would that be soluble or insoluble in water?
Solid.
So
Soluble, so we put AQ, meaning that it is soluble in water. So this is the molecular equation. So the ionic equation is next. And when it comes to the ionic equation, any ionic compound that dissolves in water will form ions, will dissociate to form ions, right? So as far as the lead 2 nitrate is concerned here, this will split up or dissociate to form Pb2 plus aqueous plus 2 NO3 minus aqueous. All right? And then as far as the sodium sulfide is concerned, that will split up to form 2 Na plus aqueous plus S2 minus aqueous. All right? And then on the product side, since this is a solid, it will not split up, right? So it will remain as PBS, solid, right? And then as far as the sodium nitrate is concerned, that will dissociate to form 2 Na plus aqueous plus 2 NO3 minus aqueous. All right? So that would be the ionic equation. So you remember how we get from the ionic to the net ionic? What do we do?
Well,
Cancel out what?
same.
Right, the ions that exist on both sides, we call them the spectator ions, right? So what would be the spectator ions in this particular case? What would be the spectator ions that you cancel out on both sides?
your 2NO3.
The 2 nitrates. Anything else?
Sodium.
The 2 Na pluses. And basically what is left will constitute the net ionic equation. So that's Pb2 plus aqueous plus S2 minus aqueous to give PbS solid. And that would be the net ionic equation. So the question says, oh, it says identify spectator ions. So I'm going to put a little note here. Spectator ions are Na plus aqueous and NO3 minus aqueous. That's it. So that will be the complete answer to this question. All right? Any questions about it? Any questions? Questions? Okay, still writing this down? All right, let me give you a couple of minutes to. Okay, so if you understood A, you should be able to do B and C Okay, so I'm gonna leave you to do B and C on your own. If you have any problems with these, let me know. Come by my office or call me on Skype, give me office hours. Okay, number 5 is asking for you to determine the oxidation number of the underlying element in the following items. Now, I'm not gonna do all of them. I'm just gonna choose one arbitrary one. I'm gonna choose this one. And basically what it comes down to in terms of, I'm gonna choose this one right here. What it comes down to is basically knowing the rules. Remember the rules I went through before. You know, any atom that is uncombined with other atoms, the oxidation number of that atom is 0. The oxidation number of hydrogen is +1, excepting in the case of hydride where it's -1. So all those rules you have to keep in mind when you're doing these problems. So in the case of H2SaSO4, the question is asking specifically for the oxidation number of arsenic, right? So basically, according to the rules, the oxidation of hydrogen is +1, the oxidation number of oxygen is -2, excepting in the case of peroxide where it's -1. This is not peroxide, so we'll stick to the -2. And I'm going to say the oxidation number of arsenic is X. We don't know what that is, right? So we have 2 times +1, because you have 2 hydrogens here, and then plus X, which is the arsenic, plus 4 times the oxidation number -2, because of the 4 for the oxygen here. When you add up all of these, that would be equal to the overall charge on the ion, which is -1. And then all you have to do is solve for X, right? So this would simplify to 2 plus X minus 8 equals to -1, which means that X would be equal to -1 plus 8 minus 2. So that's 8 minus 1, that's 7 minus 2 plus 5. So the oxidation number of arsenic in that case is +5. And that's basically how you solve the rest of them. All right, so I can imagine you need to refer to the rules from time to time, but what you'll find is that with continuous practice of these kind of problems, you get to know the rules, all right? Okay, any questions about this? Any questions? Any questions? All right, let me clear this. Let me scroll down. Let's see, oh, okay, so this question is asking, in each of the following reactions, determine what is oxidized and what is reduced. So let's remind ourselves, oxidation involves loss of electrons, reduction involves gain of electrons. Or another way of looking at it, oxidation involves an increase in oxidation number, reduction involves a reduction in the oxidation number, right? So basically what you have to do to answer this question is that you have to look at the oxidation numbers of each element involved as reactants and products and see what changes takes place as you go from left to right, from reactants to products. So if we apply that to the first problem, in the case of calcium, because it's by itself, the oxidation number of calcium here is 0. In the case of hydrogen, it's +1. In the case of oxygen, it's -2, right? Now over here, the oxidation number of calcium is +2. Oxidation number of oxygen here is -2. And the oxidation number of hydrogen here is 0, right? So obviously, calcium is experiencing an increase in oxidation number. So therefore, the calcium is the substance being oxidized, right? And then as far as the hydrogen is concerned, it is experiencing a reduction in the oxidation number from +1 to 0. So therefore, it is the hydrogen that is undergoing reduction. All right? Any questions? Okay, so if you understand this, let's see if you can answer this question. The B part. Which element is being oxidized in the case of B? Which element is being oxidized in B? Let me give you a hint. Or several hints. The oxidation number of hydrogen here is 0. The oxidation number of oxygen here is 0. The oxidation number of hydrogen here is +1. And here it's -2. That should make things a bit easier for you. So, which of the 2 elements, hydrogen or oxygen, is being oxidized? Hmm? Hydrogen, exactly, because its oxidation number is increasing from 0 to +1, so H. What about being reduced? Well, obviously that would be the oxygen, right? Its oxidation number is reduced from 0 to -2. Yes, sir.
I didn't know that the oxidation temperature outside is zero.
Well, elements by themselves, not combined with anything else, their oxidation numbers are automatically assumed to be 0. Right, so all these elements by themselves, if they're not combined with anything else, just assume that to be 0. Right? Yes, sir.
Just, get the +1 and -2 is better.
Well, you have to go according to the rules, right? So one of the rules is that hydrogen, its oxidation number is +1 in the vast majority of cases, with the exception of hydrogens. If the hydrogen is bonded to a metal, then the oxidation number of hydrogen in that case is -1. But in this case, hydrogen is bonded to oxygen, so therefore its oxidation number is +1. And then there is a separate rule for oxygen, right? If oxygen is combined with other elements in their compound, then oxygen has an oxidation number of -2. Again, there's an exception, and that will be peroxides, in which case the oxidation number of oxygen in those cases will be -1. So again, you have to familiarize yourself with the rules in order for you to be able to answer questions like these. All right,
So with the left side, how you said, the elements by themselves are 0,
right,
is that for all elements?
yeah, without exception. Right. Even if you have H2 or O2 or Na or magnesium, whatever, if it's by itself, it's not chemically combined with anything else, then basically the oxidation number is 0. Okay, I'm gonna stop here for today. Just a couple of, well, one announcement really. So you may have seen your test, your test scores that I've posted, but I'm going to scan the test, this evening and get it back to you so that you can look at it, all right? And I may have a few words to say about the test next class, all right? So that's pretty much it for today. I would suggest also, let me you see here. I would suggest that you try question number 7. Again, it's basically dealing with oxidation numbers. Excuse me. And question number 8, which deals with balancing equations, redox equations, like we've just done. So try those problems. Again, if you have any questions, please feel free to come by and see me, either in person or via Skype. All right? So that's it, folks. You too. Yeah.
2 hours.
Mhm. Good. You see here, let me go to. See that here? See. Okay, so this is. Okay, so also it's already going to that here. Well, I would. Let's see. Yeah, basically, I would suggest that you try to improve pretty much on both the assignments and the tests. So you know, basically, we're going to look at things. You're not failing upward, but if you're working towards the meeting, then you have to step up for your assignment and for the next test. Right? And come to me for help, please. Yes, ma'am.
Is there only office hours on this campus on Thursdays?
Uh,
We're not reaching that.
yeah, pretty much, because my other officers are at the. Capital. Again, so, Well, let me ask this, would you be willing to do the test after your lab this evening? Okay, work.
I'd work after.
Are you going to be at local campus on Monday or Wednesday?
Yes, actually.
Okay, so if that's the case,
I usually get there around 6 p.m., but I get there earlier.
on Wednesday, tomorrow, I'll be there from 2 to 6 p.m.
2 to 6.
Right, I've been building 2 new. Keep forgetting those.
No, this is on the silver.
Right.
Yeah. Right, I would be there 2 to 6.
2 to 6, right, I'll be in office.